Folks. So let's start session 2. So I see all the presenters are here, right? So just like, in the previous session, we will probably play the pre-recorded videos that all the authors have posted on the YouTube, and I have the updated links to them. Our session is is at par, I would say. We even maybe can advance the topics a little bit further from the session 1, right? So we will start with moving from composable to programmable, which is the paper from University of Illinois at Chicago. I believe Luke was the one, preparing the video, and I see him here, so he may answer any follow-up questions that we will undoubtedly have. And then after that, we'll follow up with the evaluating hardware memory disaggregation under delay and contention. It was from University of Illinois, this time at Urbana-Champaign. And it was a joint work with IBM Research. Some of the folks are presented here. They can answer additional questions about this work. And then finally, we will conclude with the memory disaggregated in-memory object store framework for big data applications, right? That will be presented by Robin. And this is the work from Delft University of Technology. So if you have any questions, you can ask Robin at the end of this talk. So I guess we will start with the first paper. I guess let me share my screen, right? I assume that I will be sharing my screen to present the videos, right? Okay. So let me share it. All right, you should see the, let me know if you can hear the presentation.
There is no sound so far.
Nope.
I'm sorry, you don't hear it?
No sound so far.
Oh, I'm not sure how to put the sound in the Zoom. I'm sharing. Oh, go ahead.
When you click sharing, there is a box that you have to tick.
Oh.
Hold on. So you have to stop sharing, exactly.
Oh, share sound. Okay, I found it. Okay,
yeah,
gotcha.
Exactly.
Right. There you go. Let's take 2.
My name is Luc Renambeau. I'm a research professor at the University of Illinois, Chicago, in the College of Engineering and the Department of Computer Science. I will present the work called Moving from Composable to Programmable Infrastructure. And this is mainly the work done by Zhongyu Chen, our undergraduate student, and also Lance Long, Maxine Brown, and Andy Johnson at the EVL Electronic Visualization Lab. So in 2019, we got awarded a grant for a composable platform inside the College of Engineering, and from the National Science Foundation, and so that let us purchase a composable infrastructure composed of 24 compute nodes, a lot of high-speed networking, a bay of storage, SSD storage, and NVMe SSD storage, and mainly 64 GPUs, 32 high-end GPU and 32 mid-range GPU. And that compose the 2 racks of hardware that you see here in the picture. And so in the center, you see the compute nodes, and above and below each rack, there is a PCI Express chassis that hosts the SSD, the network card, and mainly the GPUs inside to be composed, basically, and with a compute node. And so the composable system that we purchase is a liquid system, which is basically a programmable fabric based on PCI Express. The switch fabric. The fabric switch that you see here is a PCI Express controller that let someone build machines out of all the components that you have in the rack. So you have the compute node at the bottom here, for instance, and with daughter card connected to the chassis. And then we have various expansion chassis for the types of devices that we want to host, like a networking card, NVMe SSDs, and GPU racks, basically. And so the vendor here, Liquid, provides a very nice user interface, a graphical user interface. It's all web-based, and it gives us a comprehensive view of the user interface at a very high level. And you can create groups of components, and then an administrator can come in and create machines based on the available hardware. In our case, in the Department of Engineering, we had very varied requirements that change very quickly over time. If there's for instance, a deadline for a workshop or conference, people need a lot of GPU and various machines containing GPUs, and so the user interface becomes a bit cumbersome to manage, and also it's not a user interface that we can deploy to the end users. It's really an administrative interface. And it's something that we cannot automate also. And so when we want to do very high level tasks, such as I want to build 10 machines with the same configuration, it's very tedious to do that with the graphical user interface. And so in our case, for academic research, we really had different need and different way of integrating composable architecture inside our workflows. So we came up with the idea of building a high-level API, which is and let us expose programmable hardware to more people. And so that could be an infrastructure engineer, but also data scientist at some point. And so it's a simple APIs that let us compose machine and decompose machine, and so freeing resources. And hopefully that could be vendor independent. If there was different vendors with different low-level API to compose hardware, it would be nice to be able to integrate those various API into a common high-level API. Also, our API support multi-rack operation, and so that's something that was important to us because we have basically 3 systems where each rack is a different fabric, and also the development kit that we have, a smaller system, is also its own rack in some way. So we wanted to, and so the most common programming language for scientific workflows is really Python inside programmable notebook. And we have a lot of machine learning users and users from the physics department or the mechanical engineering. And so Python is, and Jupyter notebooks are really the predominant way of programming and describing workflow. So it felt like the right match to expose that high-level API into a Python module that we can load into a Jupyter notebook. And so the functionality that we want to have, it was basically fairly simple in some ways, being able to compose machine and to see the resources attached to the machine, and on the other hand, seeing all the resources available. It should be easy to see the list of GPUs, the list of SSD, and to see or the networking interface cards that are available. And as I said, we want to be able to see the different fabrics into one API. So again, being able to compose, modify, and delete machine, and also at some point to be able to monitor the system. And once we have those low-level functionality, we want to be able to, for instance, to save and restore whole configuration for the whole rack or for multiple rack at once. And it's something that, for instance, the vendor didn't address at all in the first user interface that we were provided. And that's something we have added, and that's been really, really useful to be able to, for instance, shut down the whole system for firmware upgrades of the PCI Express fabric, and then reload it in a few commands. And so the system is composed of servers that would talk directly to the hardware, to the low-level API of the vendor, and then a set of clients, basically Python modules that you would that would connect to that server and send commands to build and to build machine and free machine and attach devices and so on. And so how does it look like? So we have a series of screenshots of our system inside the Jupyter notebook, where first you just are going to provide the URL for the server that connects to the backend system, providing a username and password and the fabrics that you want to talk to. And then as soon as you have the connection established, you can list the fabrics and get information about the fabrics that you are connected to. And then, so then we have a series of high-level functions that we implemented, such as showing all the machines that are currently built into the system. So here you see for a given fabric, we have, like, for instance, 3 machines here built, like Demo, Astrolab, and Compose with the machine ID. With another function called show all devices, you can get a nice table of all the devices available. So the CPU, which is more or less the compute node, the SSD, and the GPU. And so that's all the devices in the system, but you can also show all the available devices, devices that have not been attached to any machine yet and that are available to compose a machine. And so you can see the device, and to compose a machine, it just comes up to give it a name and a list of devices that you want to build, and then it's just called to compose machine and pass a device list. So here, that call, in fact, in that very specific case, should fail because yes, you see there's no, for instance, no GPU available in the device in the available list. So that call would fail, but that's something we can respond to. And so once a machine is built or composed, we can decompose it with just a simple call to decompose machine with a fabric ID and a machine ID. And at runtime, we can add and remove devices to a machine through PCI Express hot plug. And so here, for instance, we can remove device. So we can remove a GPU and an SSD from a machine dynamically. And something we have been doing a lot is adding a GPU to an existing machine. That's a workflow that we see a lot, where a user wants to scale their experiment from 1 to 8 GPU, for instance. And so our system administrator or the user, him or herself, can add directly a GPU at runtime into the machine and conduct their experiment. And so that's been a great help for our system administrator, and we're interested to deploy that to the user, to being able to integrate it through a few commands directly into their workflow, to be able to compose the machine and then run the experiment. That is driving, for instance, the vendor. We have been in close contact with the vendor, and that's inciting them to develop an SDK and provide a better SDK. And also it should help with integration of other workflows such as Kubernetes and Slurm. And so the software is available here. COMPSYS structure is the name of the project. It's on GitHub, and you can have a look at it and use it. And so you can email me for more information. And I'd like to thank the NSF for the funding. And also please look at the other papers that we have in the session about our experiences using COMPSYS, our composable hardware.
All right, folks. So I think it was a very interesting talk about the liquid technology and its applications in the University of Illinois. So let me start with a few questions, and then you can raise your hand if you have more. So the first question here to look is, do you consider misuse of the API, right? Like if users, for example, try to plug everything into one machine, right? Like, can there be situations where there may be mistakes in which APIs are used, right? Like, or maybe you have encountered it in the field, right? As you were using the system. So like anything you can say about that?
Mm-hmm. Yes, definitely. Right now, it could be misused. We haven't put not a lot of safeguard. And so far, our most user has been, in fact, Lance, as a system administrator, has been using it. And yeah, if we were to deploy that more to the end user, we would have to put more safeguards. Inside specific to the liquid hardware, there is a notion of groups that you can define. So not all the devices are available to everybody. You can define groups of hardware at a high level. And then the idea would be to assign groups of hardware to research groups, for instance, or to a faculty or something like that. So for a given time, you can say that faculty can access those 8 GPU or can compose only that subset of hardware. So that's one thing would be nice to integrate. Otherwise, yeah, all permissions and things like that. It's open right now, definitely.
I see. Thank you. Okay, so another question I had is, so what is your experience regarding sizing of the machines by the user? Do they get it right, over or under provision, right, in terms of what they need for their workloads?
Yes, it depends. It's sometimes if the requests come from a faculty, they might sometimes over ask or something like that, over provision. They say, oh yeah, we need 8 GPU and we need the Hay100, which are $10,000 a piece. But on the other hand, we have students, undergrad that come or graduate student, and then it's a learning curve also to scale their model to even like multiple devices. Like going from 1 to 2 GPU is often hard. So yeah, I think we encounter both over or under provision. Sometimes people, even like for the storage, for the SSD on demand, they say, oh no, I don't need data. And then the next day they come and I need X terabyte of storage. And that's where I think the composable hardware is nice, because then we can fairly quickly respond to those demands. We can then, oh yeah, we will attach an SSD to your machine because you need the local storage, or somebody now wants to transfer the data. We have a lot of networking research going on in the lab. So something we haven't talked a lot is the network interfaces are also composable. So we can attach a 100 gigabit link directly to the node if suddenly somebody needs to transfer a big data set, for example.
Right, exactly, yeah.
Really quick on that. Now that we've had a few years of history too, we've discussed like adding recipes for users. So here's like a recipe for what has been successful historically for a user's type of application. So building out more models like that too.
Yes, things like a user that undergrad might not know, even graduate student, but we think you need probably that container, like this PyTorch container, and start with a mid-range GPU on one node. We can compose that very quickly and come back next week and ask us again, for instance.
Yeah, makes sense. Okay, so I think that we have more questions in the chat. So folks, if you can answer it, we have to move on, unfortunately, but folks continue asking questions in the chat. That's more than welcomed. We will move on to the next talk. Let me actually share it.
So no, for now.
Hi, I'm Archit, and today I'll be presenting our work on evaluating hardware memory disaggregation under delay and contention. So in hardware memory disaggregation, each data center node is either a borrower node or a lender node. And the borrower node tries to borrow memory from the lender node. To do so, the CPU tries to access memory on the lender node and it generates a cache miss. This cache miss is sent to the disaggregated memory NIC, which is forwarded on the shared network and reaches the lender node. Hence, remote memory access happens at a load store granularity, and this exchange is supported by a cache coherent interconnect such as CXL or OpenCAPI. And as the access happens at the cache line level, no changes are required in the operating system or application. So the state-of-the-art memory disaggregation is supported at the rack scale. For example, Thymus Flow, which is supported by OpenCAPI, and Elastic.Cloud, which is supported by CXL. However, there are proposals to scale beyond the rack, largely driven by the availability of more memory. And the latest CXL 2.0 standard also introduces switching support to enable memory disaggregation beyond the rack. However, there are problems which are introduced by scaling disaggregation further. For example, there are new failure modes which cause higher latency introduced by network faults or congestion, or resource contention where multiple applications are competing for limited memory and network resources. So our goal in this work is to characterize the impact of scaling using existing rack scale systems and understand implications for resource allocation mechanisms in the next generation systems. So to do so, we have developed a delay injection framework that emulates switched network latency by introducing delays in memory accesses. And we also introduce multi-tenancy, so where we evaluate the impact of resource contention by running multiple contention-inducing applications and seeing how the application and system responds. Our experimental system is COMPSYS Flow, which is a two-node memory disaggregation prototype, as shown on the diagram on the right. And we developed the delay injection framework, which arbitrarily delays remote memory accesses to whatever value we want it to be. And the mechanism is based on modifying the disaggregated memory NIC, which we have implemented as an FPGA. So the FPGA communicates via axis streams, and we have implemented a mechanism that can hold these axis streams for fixed intervals of time equal to period. So higher values of period will introduce higher delay in the remote memory access. So next we want to figure out what level of delay can the system handle at high delay values. So we realize that the system remains functional up to 4 milliseconds of delay injection, and this high delay value corresponds to greater than 99th percentile latency in data centers. However, at such high delay values, we observe severe performance degradation. So if you look at the figure on the right, it shows the impact of a 400 microsecond delay on performance degradation of different applications. So the BFS application in Graph 500 degrades by more than 2000x. The single source shortest path degrades by more than 1800x, and Redis performance degrades by 1.73x. So we observe that the CPU is resilient to extremely high delay values. However, high delay values cause significant performance degradation that violates service level agreements for applications. Previously, we saw the impact of high delay values on system and application. However, now we try to answer what happens at lower delay values. So we injected delay values for periods between 1 and 40, which approximately corresponds to delays ranging from 1 microsecond to 16 microseconds. And even at such low delay values, we observe significant performance variation. For example, the performance of BFS degrades by more than 10x at period 40. Also, interestingly, there is significant variation in performance degradation between applications. So between Redis and breadth first search, there's almost a 50x degradation in difference in performance degradation at the same period value. So our conclusion is that the variable application performance degradation happens under increased memory latency, and due to this, it would be a good idea to want to enable quality of service features and resource control mechanisms. Next, we try to understand the impact of multi-tenancy in memory disaggregated systems. So we try to create two contention scenarios to demonstrate how multi-tenancy might affect performance of applications. So in the scenario on the left, we have multiple applications running on the borrower node and no application running on the lender node. And each of the applications on the borrower node tries to borrow memory from the lender node. So we notice that because multiple applications are contending for the same network link and remote memory, there is a drop in available bandwidth as the number of applications increase. At the other scenario, we create as lender side contention, which is multiple applications are running at the lender node and single application is running on the borrower node, which is trying to borrow memory from the lender node. So in this case, the applications are contending for the same memory, but they do not contend on the network. And we observe that even as we increase the number of applications on the lender node, there is not any difference observed in the available bandwidth at the borrower node. So we realize that network latency dominates over memory contention at lender node, and this serves as an opportunity to enable contention-aware job scheduling mechanisms to favor applications which are highly sensitive to memory latency. To conclude, we use the delay injection framework and multi-tenancy experiments to infer characteristics about the disaggregated memory system. And our main conclusions are, so first, disaggregated memory systems are resilient to timeout-induced failures. Second, network delay can lead to significant performance variation in applications. And to prevent this, we need a quality of service based resource control mechanism at the network and the system level. Thirdly, memory contention at the borrower node is much more significant than the contention at the lender node. And this can be used to drive contention aware scheduling mechanisms.
All right, folks. So very interesting work as well about the message flow-based design. So once again, let me start with a few questions here. So the first question, so on the slide, that was titled resilience assessment, right? You mentioned that the system remains functional to up to 4 milliseconds delay injection, right? So the question is, what caused the system to break past that point, right? Like what was it timeouts? Like what is your intuition of like why 4 millisecond was like the breaking point?
Yeah, so the disaggregated memory NIC, which was implemented as an FPGA, was simply not detected by the system, because just to set up the remote memory accesses, you really need to send some control commands to enable the setup, and the control commands themselves were delayed to a high value. So the FPGA was no longer responsive, and and a remote connection could not be established.
Yeah, it's interesting that in your work, CPU was very tolerant of high latencies. That's perhaps encouraging for CXL and technologies like that. Another question I had is, so on the slide after, resilience assessment, so you've presented the data for the workloads that you've tested, right? Which included Redis, BFS, and the SSSP. The question is, what caused the Redis to have less degradation in particular versus those graph traversal benchmarks, right? Like BFS, do you think?
Right. So I think that with Redis there is a component of where it communicates via the TCP stack by socket communication. So the bottleneck in serving requests is not actually memory, but at the network stack dominates, and therefore even if there is higher memory latency, it's sort of hidden by the network costs.
I see, makes sense. The last follow-up question, where have a few more minutes, is so you've mentioned that you've concluded your talk about with understanding the need for the contention-aware policies, right, for the applications that share, for example, memory resources. Like what type of contention policy do you think could be applied here, right? How would you prioritize maybe the workloads? Maybe you do some other type of contention management. What do you think can be the future here?
Right. So what was interesting about the experiment was that despite having many memory and bandwidth intensive applications at the lender node, the performance of the application that was borrowing memory was not affected. So essentially, if you have to schedule two jobs, one which can afford, say, latency, and one which is very bandwidth intensive, you can a good idea might be to schedule the job which is sensitive, not as sensitive on the borrower node, and the job that is bandwidth hungry on the lender node. So that way you avoid contention or creating any sort of bottlenecks for both applications.
I see.
So, and I think you can create more scenarios like this where you can schedule more intelligently so that you avoid memory latency.
Yeah, makes sense. I mean, I think that that can be applied quite well in the CXL 2.0 and beyond case. So yeah, makes sense. I think Sudan asked a question in the chat. So Archit, if you can once again answer it in the chat, we have to move on, unfortunately. So let me start presenting the last but not least talk. Hold on.
Hi there, I'm Robin from Delft University of Technology, and I will present to you our recent work for the Accelerated Big Data Systems Research Group. Before I introduce our solution, I'd like to quickly explain the context of the problem we are addressing. Big data application developers, of course, want to leverage the benefits of memory as much as possible, but often available memory within compute nodes is limited even if data center as a whole is ample. This obviously clashes with the continuing trend of the increasingly large data volumes that are accessible to us. In order to overcome local memory limitations, big data frameworks like Apache Spark allow the developer to divide their dataset into partitions and to distribute these partitions across compute nodes. The compute nodes can then intercommunicate over the local network whenever necessary. This works great while mostly operating on local data. However, quite often we need to combine data from multiple partitions. The type of operation which requires input from more than one data partition to complete is called a wide dependency operation. The diagram aims to explain this further. Imagine the blocks are data partitions, and in order to calculate the green block, we need input from all the blocks that have arrows pointing towards it. Examples of such operations in Apache Spark are the group by and certain join operations, which are notoriously expensive. The problem with wide dependency operations arises when operating on distributed datasets, as accessing remote partitions incurs a latency penalty for having to cross the local network. Moreover, shuffling data across the network might require a node to expel data from their local memory, degrading performance further. Recently, the COMPSYS flow memory disaggregation framework was introduced, which allows compute nodes to directly access an adjacent node's memory regions at minimal cost. This is done by exposing a disaggregated memory region, which is serviced by the COMPSYS flow hardware and software interface to guarantee consistency and performance. If we connect two nodes both ways, memory disaggregation can function similarly to shared memory across nodes. This could help solve our wide dependency problem by allowing the combined processing power to act on the entire data set in memory. However, in COMPSYS flow, some cache coherency intricacies prevent us from bluntly treating it like shared memory, the details of which can be found in our paper. With some extra work though, we can still use the technology to our advantage. For this, we build on the Plasma Object Store, which is part of the Apache Arrow framework. It provides a shared memory service for applications to store and retrieve immutable data objects. By providing a standardized format and minimal serialization overhead, it delivers very high performance. It works as follows. Applications can create objects with identifiers in the Plasma Store and commit their data to shared memory. After this, other applications can request a buffer with the object identifier from the Plasma Store to access the memory location of the immutable data. By combining COMPSYS flow and the Plasma Store, we aim to provide a solution to improve performance mainly for wide dependency operations, but not limited to them. For this, we integrated memory disaggregation into the Plasma Store such that clients can access objects on remote compute nodes. We use the immutability of the data objects to our advantage to ensure that cache coherency issues do not arise. In this, we provide a framework that we hypothesize can provide improved performance for wide dependency operations with simple programming models. In order to integrate these technologies, we modified Plasma to allocate objects in disaggregated memory and added an RPC interface for orchestrating existing objects between remote Plasma stores. For example, when creating an object, the Plasma store makes an RPC request to ensure uniqueness of the object identifier across the distributed system, as otherwise applications might not be able to access all objects. Creating and retrieving local objects then works the same as it did before. However, the behavior is different when a process requests a remote object. The local Plasma store will receive the request and will not recognize the object identifier. The local Plasma store will then relay the request to the remote Plasma store. If the remote Plasma store recognizes the object, it will return a buffer with the object to the local Plasma store. The latter then forwards this buffer to the requesting process, which can then retrieve the object data from disaggregated memory and continue its way. To prove the system, we set up micro benchmarks to measure the full round-trip latency of fetching an object from local and remote disaggregated memory separately. These measurements include both access latency and data throughput. The benchmarks vary the sizes of the fetched objects across 6 orders of magnitude to capture any potential differences. We can then compare local to remote performance over the different benchmarks to identify trends. The results are expressed as throughput and shown in the diagram here. The data for the smaller object sizes shows larger variability and appears to be influenced by boilerplate code significantly more than benchmarks 4 to 6. For the latter, the measurements converge neatly, which is indicative of reaching memory bandwidth limitations. The measurements demonstrate that remote throughput is close to local across the board, which is a promising result. Performance also appears competitive with existing state-of-the-art RDMA technologies. Some main hypothesized improvements to the system could be provided by a more intricate communication interface between remote Plasma stores, improved memory allocation, and advances in underlying memory disaggregation technology, like memory inception as announced in Power 10. With that, we conclude that we have successfully demonstrated our novel memory disaggregated object store framework for big data analytics purposes. Furthermore, the benchmarks indicate that performance for remote object fetching is close to native, demonstrating the proof of work for our framework. And lastly, the paper provides a stepping stone for future research to improve performance of the framework to integrate it into existing big data workflows. Our main contributions in this paper are the proposal of the framework, the benchmark results, and extensive considerations and recommendations for future work. Additionally, the work is open source and I invite everyone to contribute. With that, I would like to thank you for your attention.
All right, great talk. Let me start with the questions here. The first question is, so have you done any scale out versus scale up experiments, right? So for example, you can have only one Plasma process run and using both local and remote memory, right? Will this simplify the communication and hence reduce object access time?
Sorry, could you repeat what you mean by your?
Like, for example, so let's say you have an example, you have only one Plasma process running and using both local and remote memory, Like so the same plasma process is using both local and remote memory, right? Will this simplify the communication and reduce, and maybe it could reduce the object access time as a result? Christian can actually, clarify the question.
Yeah,
he was
yeah,
no, I do think I get it. Okay.
So if you distribute this plasma, okay, here you show that if you are distributing the plasma on top a number of nodes, let's say 2 nodes. Why do you distribute it on 2 nodes? What's the need? Do you do it for getting more memory, like using memory on both nodes?
So due to the cache coherency characteristic of the system, if you write to remote disaggregated memory, it's not necessarily the case that both nodes will read the same values.
And this I understand, but in your paper it looks like that before you write, you ask the plasma object process. Sorry, tell me where the object is, and then then the application accesses the object, right?
Yes.
It looks like you have replicated plasmas. So basically, the plasmas talk to each other to figure out where the object is. Couldn't you just have one plasma project?
Yeah. So the advantage
of remotely ask where is the object, and then you access remote memory. So the access to remote memory, you keep it as it is right now, so that you avoid coherence issues. Have you done any of these experiments?
Yes, thank you. So the advantage of this architecture is that you can do processing on both compute nodes. So that's what I was alluding to earlier, with if both nodes may not read the same values for when they write to each other's disaggregated memory. So in this, if you have one instance of plasma, you can utilize the compute resources of this one node on a large memory volume. So that both the local volume, local memory, and the remote disaggregated memory. Whereas if you have this architecture with multiple plasma stores on different nodes, they can do their processing in parallel. Does that answer your question?
Yeah, but maybe I'm not fully aware of how plasma works. So I'm not 100% sure of which type of computation that the plasma do.
So plasma,
if there is any computation.
Yeah. So plasma is just a generalized way to store big data objects. So this can be anything. So for example, right now there's people from my research group looking into applying it to existing genomics big data pipelines. And the goal is to see how can we parallelize this and actually apply the plasma framework in a distributed way so that we can simultaneously utilize the resources from multiple nodes in an easy programmable way.
Okay, I understand. Okay, makes sense. I understand.
A follow-up question on, so adoption of the plasma, right, to the Mesos flow-like setup. So does plasma have any support for atomics, right, for arbitrated access across multiple processes, right, or agents, right? Let's say they're working on the same memory or the same variable. Are there any locks that are supported, maybe, mutexes or something like that, right? So, and if so, like, are atomics or barriers supported in any way there? I'm just curious.
Yeah. Okay. Thanks. So these systems are not included in Plasma or in the original Plasma. Also, very limitedly in our version. And that is due to the fact that we're dealing with immutable data objects. So you don't really need the mutexes. And that's exactly why the system works well for big data purposes, but only if you can get away with using immutable data. And that's also kind of what our system leverages. Because if the data wouldn't be immutable, you would have a bunch more issues with coherency indeed.
Right, makes sense. Okay, sounds good. And I think that for the CXL, at some point, globally shared memory, or for Gen Z, is an interesting concept, right? So at some point, it should be thought about, right? But I see what you're saying here, like on the big data needs. So I think that we're almost out of time. So if folks, if you have any other questions, we had the lively discussion so far. If you had any other questions, post them into the chat, and the folks, the authors will have time to respond. Other than that, I think that we're done here with the session number 2. Thank you, the presenters, for the wonderful talks and being gracious enough to answer the questions. So we will have the break, 15-minute break, and then after that we will resume with the panel discussion on current trends and composability. Should be pretty interesting discussion there. So have a great break, you guys, and we'll see you in 15 minutes. Thank you.